My name is Charlie Whitman. I'm a systems engineer at JMP. I've only been here for some months, but I was in industry, mostly semiconductor industry. I worked as a reliability engineer. So, and for a lot of that time also, I was using JMP. I was a JMP customer. So I hope that in my talk here, I'm going to be able to explain a lot of things you'll understand, and hopefully this will be something that's useful in your work and I can answer any of your questions. Just to save on bandwidth, I am going to turn off my video. Here we go. Okay. So the title of the talk is Everything You Ever Wanted to Know About Accelerated Life Testing, ALT, but We're Afraid to Ask. So we're going to be covering a few different topics here. First, I just want to start off with what is ALT? An ALT is basically a method we use for stressing parts so that things happen faster. We just want to make the clock run a little faster. Okay? And the cool thing here about ALT and a lot of statistics is that you can apply this to any part or product that degrades under stress. So my background is in semiconductors, so the examples I'm going to talk about today, I'm going to talk about some capacitors and things like that, but this again would apply to many different types of products. Okay. So again here, time is accelerated. It's because what we're going to do is we're going to use stress levels that are typically going to be much higher than use conditions, take data from those high stress tests, and then extrapolate that to a use condition. And a big assumption that we have to make here is that whatever the failure mechanism is, or whatever the degradation mechanism is, it's not changing. We're not introducing some new failure mode. So you want to go to higher stress, but you don't want to go so high that you change everything, because when you do an extrapolation with data using a different failure mechanism, your extrapolations won't be worth very much. So just to kind of demonstrate what I mean by the stopwatch here, the accelerated time. So here we have a couple of stopwatches, and the one on the left is for low stress, and the one on the right is for high stress. So if I start the clocks, you can see that the high stress time is just moving more quickly. And I can kind of show you what that's going to imply in some examples coming up here. But this is the bottom line. All we're doing with the higher stress is we're making the clock run faster. Okay. So why would I want to use accelerated life testing? Well, we're always trying to qualify new materials or processes, designs, etc. And we want to do this in a practical amount of time. Sometimes the expected life of a product is so long, it doesn't make any sense to try to test at use conditions. You want to test at some high stress and then extrapolate to use conditions. Another cool thing you can get from ALT is you can make predictions. So I can predict what's the probability of failure or what the failure quantiles are at use conditions from my high stress data. And I'll show how to do that. And also, something I think is pretty cool is that you can get a reliability map. And this reliability map is something like a response surface. If you're familiar with the design of experiments, it's the same kind of an idea. I'm going to get a reliability map, and that's going to allow me to make trade-offs between the stress conditions. So let me first show you just a probability plot. So let's imagine that we put some parts on test. Maybe these are capacitors, and we run them at different voltages, say 50, 75, and 100 volts. And we have these fail according to a Weibull distribution. Here we have Weibull probability versus time. And so at very high stress, at the highest stress, 100 volts, these parts are lasting, I don't know, say less than 10 hours or something. Then as we progress to lower and lower voltages, say 50 volts, parts are lasting, several hundred or maybe 1,000 hours, something like that. And so what we can do in JMP is take this data that we've gotten at very high stress and then extrapolate that to our use condition. Maybe our use condition is much, much smaller than our stress condition. So this is going to be, say, 10 volts. And we can predict now from this plot, we can make a prediction. What's the time for 50% of my population to fail at use condition? That might be something you're interested in. So here it looks like that would have a median time of failure of 4 times 10 to the 10th hours. And that is a big number. Holy cow, that is a big number. This is like, a million years or more than a million years. And so it's simply not practical to try to test the use conditions. We're kind of forced to go to higher stress and then extrapolate to use conditions. Okay. Another cool thing here, as I mentioned, is getting what I call a safe operating area. And this is kind of a contour map, I guess. Here I have a plot. This is the log base 10 of the failure time. And I have my two stresses I care about. I vary voltage and temperature. And what you can see here is there's a large green region where we say the reliability is high. This is a safe place to operate. And over here, when the stresses get high, when the temperature gets high and the voltage gets high, it's not safe. This cutoff, maybe this is a corporate goal. Since this is log base 10, this region is marked by 10 to the 6th hours or a million hours. So if you operate at too high a temperature and too high a voltage, the median time of failure will be less than 10 to the 6th. Operate down in the green region, the median time of failure will be larger than 10 to the 6th. Right? And you can also use this to make trade-offs. Let's suppose a customer or you have a designer and they say, well, we really want to start to operate the part we have at 60 degrees C. You can say, that's fine. Operate it, you can run it at 60 degrees C. Just make sure that the voltage doesn't get too high. Or same thing, they want to run it at a high voltage. Again, that's fine. You can run it at a high voltage, but just don't run it at too high a temperature then, because you'll start to get into this red region. And this example I've given here is for voltage and temperature, but it could be anything, any other stress. This could be relative humidity and temperature if you wanted. Right? So here we have our safe zone, right? I want to make this distinction. The safe zone is in green, and over here would be our danger zone. So if you are running a process or running a part, and the temperature and the voltage start to get too high, you're on this path. You're kind of on. This is the highway to the danger zone, and so you want to avoid the highway to the danger zone unless you're Kenny Loggins or something. Okay, let's move on. So what makes ALT analysis different? Well, one thing that's true is that data can be censored. I'm going to show some examples of censoring. That's also true for just reliability analysis in general, but it's certainly true in accelerated live testing. You can have censored data. And also, just like for reliability in general, the failure distribution has to be where t is greater than 0. So, for example, the log normal or the Weibull are typical choices for the failure distribution. Something like the normal might not be a good choice because the normal will allow negative values of time. And it doesn't make any sense to have negative time. So we're kind of constrained in our choice of distribution. Another big difference for ALT is almost always some sort of extrapolation is going to be required. Again, we're going to be running parts at high stress and then extrapolating to use stress. Just to show you what censoring means, censoring does not mean that people are using bad words or something. For example, here we have, this is a right censored. So let's say we have 3 parts on test. Okay. Part number 1, we see that it fails after 10 hours. Part number 2, that fails after 15 hours. Part number 3 goes to 20 hours, but for whatever reason we have to stop the test because we have a queue, a test queue, and the next test has to go into place. So we stop the test and we find that part number 3 has not failed yet. It would have failed at some point if we had allowed the test to continue. We don't know exactly when. So the failure time is greater than 20 hours. That's a censored data point. And so in JMP and other software as well, there are methods available to you to treat this censored data. You don't have to exclude it from your data. Say, well, I didn't get a failure, so I'm just going to not use it. Or I'm not going to put in some fictitious time. I'm going to make up a time. You don't have to do that. You can use the actual censoring time here, this 20, in the data, and JMP can handle the analysis. Another type would be interval censoring. Right? So again, part number 1, let's suppose we inspect every 5 hours or something. We have parts in an oven, and every 5 hours we're going to go in, take them out, and inspect them to see if they have failed. So after 5 hours, we didn't get a failure. After 10 hours, we didn't get a failure. And then we go to 15 hours, and then the part has failed. So it must have failed somewhere between 10 and 15 hours. We don't know exactly when, but it did. So it's interval censored. It failed somewhere in this interval. Part 2, same thing. This time it failed somewhere between 15 and 20 hours. And part 3, it failed after 20 hours. So you could say, well, the interval here would be between, say, 20 hours and infinity, right? And you can actually do that in JMP. You can say that I don't know the other upper end here, so I can use infinity if I want to. The other thing here is left censoring. Left censoring is less common in industry. You can imagine, before we start a test, I have 3 parts I'm going to put on test, and I'm going to do an inspection of them at t=0. Before I start the test, I'm going to make sure they're all working, and then I start the test. So you probably wouldn't be starting a bad part initially. If it's failed, you're not probably going to put it on test. But in the biological sciences, this might happen. Say, for example, you're want to test a treatment for a disease, and you want to see if this treatment will delay the onset of a disease. But a patient comes in who's part of your protocol, and if they already have the disease. When did they get the disease? Well, I don't know. It happened sometime before t=0. That's where you would use left censoring, but that's not very common for our case here. Okay, so let's talk a little bit about constant stress. And as I mentioned, there's a whole bunch of different stresses that can be used. Temperature, where we've used the Arrhenius rule, voltage, current, humidity. We put parts in an oven or something like that and ramp up the humidity to see if what the effect on corrosion is. This could be a mechanical test. We could be dropping things. We could be have some vibration with some amplitude and frequency, etc. So there's lots of different types of stresses. But I'm going to focus on 2 most common ones, and those are the Arrhenius rule, and we're going to do a power law using voltage. So here, the Arrhenius model basically talks about temperature. And the idea is that when the temperature goes up, bad things can happen. The part starts to degrade. And there's a basic equation that we use to describe it, and that is the time to failure is equal to some constant, and then it's exponential with temperature. So A is a constant, EA is called the activation energy, T is temperature, and K is Boltzmann's constant. And you'll notice here that I can take the log of both sides of this expression and get something that looks like the point intercept. Okay, so I have a point intercept formula. Here's my intercept term, B0, and my slope is B1. So here, B0 is going to be log of A. B1 is going to be EA. And my X can be 1 over KT. That would be one way to parameterize it. And so we're going to see this type of an equation in the output in JMP. So I just wanted to make sure you were aware of it. So here are some Arrhenius results for some simulated data. This is actually an Arrhenius plot. I have time to failure over here on the y-axis. I have temperature over here on the x-axis. And you can see that the spacing here between the temperatures is not constant. So this is 10 degrees here between 90 and 100. This is 10 degrees between 170 and 180, but that spacing is not the same. That's because we're talking about 1 over temperature, inverse temperature, and a transformation has been done. And since we did a transformation, the spacing is not the same. But here we have some log normal data, okay? And I have 3 different temperatures I ran at, 150, 175, and 200 degrees C. And you can get an idea of what the failure times are here. At 200 degrees, parts fail between about 10 hours and 100 hours on up to 150 degrees C. And here parts failed anywhere between 1,000. And you can see this triangle here. And that triangle indicates that we have a sensor data point. That's how JMP treats sensor data. It makes a little triangle there for you. And again, even though we've stopped the test here, this looks like at around 2,000 hours, we can still take that into account when we do the analysis. Again, we don't have to throw out that data. And now with this data at high temperature, high stress, we can do an extrapolation to low stress. And what we're going to get is we're going to know what the distribution is at our use condition. In this case, I chose 100 degrees C. And I know the distribution. I know everything about this. So that means I can say, what's the probability of failure at 100 degrees C after 1,000 hours or after 100,000 hours, something like that? Or how long will it take 10% of the population to fail here? Those are two basic questions that you might want to ask, and all can be answered from this distribution. Okay? Another way to look at it is the same data, but I'm looking at it a different way. I'm going to use a probability plot. This is kind of like the one I showed before. And we have our three different temperatures. So 200 degrees C is in blue, and it was failed, again, failing according to a log normal distribution. And it looks like it's fitting pretty well. It's good to see that the data fall along a straight line pretty well. Then as we go lower in temperature, parts are lasting longer. And we're clipping here at 2,000 hours because we have a queue, we have a test queue. And we're only allowing 2,000 hours. After 2,000 hours, I'm sorry, that's long enough. You have to stop that test. If it's failed, it's failed. If it hasn't failed, then okay, we'll just take that into account when we do the analysis. So it looks like about 60% of the population has failed by 2,000 hours here. And so what we're going to do again is we're going to extrapolate then to our use condition of 100. And you can see what I can do is I can tick off, right, my failure time at a particular quantile. So let's suppose I care about the time for 10% failure, right? So how long will it take 10% of the population to fail by or at 100 degrees C? And I can draw a line over here at 10%. It intersects, I drop down, and I get about 1.8 e to the 5. That's about 180,000 hours. Okay? And I get that value from this data over here, from this output. So here's our intercept term. This is our log A or B0. This is our activation energy, 1.4 eV. And this is the shape factor. The shape factor is related to the slopes of these lines. And so the shape factor is assumed to be constant here across these different temperatures. And so we know the shape factor is going to be for use conditions. So if we know the shape factor of use conditions, we can also put in a value for T. We could put 100 in for T here. We get an expression. We'll know what mu is. We know mu, we know sigma, we know everything. So we can now predict what the probability of failure is at a given time or what the quantile will be. Right? Another thing you can do in JMP is do some custom estimation. I'll show you how we do this. But suppose you have some particular probabilities you are interested in, like the time to 1% failure, time to 10% failure, time to 50% failure at your use condition. So I'm going to put in 100. And what you get out are these times. It'll tell you the time to 1% failure at 100 degrees C is about 100,000 hours. And you even get some confidence bounds on top of that. Right? I can do the same thing for these other quantiles, and I can get estimates of the time to failure. I can also reverse the question. What if you have a corporate goal is, we want the probability of failure at 100,000 hours and use condition to be really small. So you can put in that value. You can say, well, the failure time is 100,000. The temperature is 100. What's the probability of failure? Well, the probability of failure looks to be less than 0.9%. So that's pretty low. Maybe that's acceptable. Maybe it isn't. But at least get that information out. Okay. So I'm going to walk through how I would do an Arrhenius analysis. Right. All right. So let's see. So here's our data table, and I can take a look and see what the spread in my data is. And I have my three temperatures. I have 150, 175, and 200 degrees C. And I have my failure times, and that goes anywhere between 10.5 hours and 2,000 hours. Again, remember, we're clipping at 2,000. We're stopping the test at 2,000 hours. I have another column but with a sensor indicator. This is my sensor column. And so for the very first part, we ran that part at 150 degrees C, and the failure time was 1,468 hours. So that gets a censoring value of 0. 0 means it failed. The next part, also at 150 degrees C, that went to 2,000 hours. We pulled the part off, we inspected it, it had not failed. So that is censored. Then the censoring gets a value of 1. And then I can just go on down for all the parts, and I had a total of 75 parts I tested here, and I have all my failure times, all my temperatures, and my censoring column, my censoring indicator. Okay. So now I want to do an analysis on this data. So what I would do is I'm going to go to Analyze, Reliability and Survival, and then I'm interested in Fit Life by X. X is the stress. That's what it means. So fit life by temperature, fit life by relative humidity, fit life by voltage, whatever. That's my stress. So I click here. And this is kind of your typical dialogue that you get in JMP. You have your column names over here on the left, and you're going to populate. You're going to tell JMP what means what over here. And so what's the time to the event? The time to the event is my failure time. So that goes here. X is my stress. What is my stress? My stress is temperature. So I click X. I have to tell it censoring. So here's my sensor value here. That goes here. Sensor code 1, this is the default. So a sensor code of 1 means it is censored. I'm going to use the Arrhenius model. So Arrhenius in Celsius, my temperature is in Celsius. So I'm going to use that. I can tell JMP what my use condition is too. And I know my use condition is 100. So I'm going to enter in 100. And I know I'm going to know, or I assume my distribution is log normal. So I'm happy with all this. I'm just going to click OK. And here is my scatter plot, or my Arrhenius plot. And right now, you're not seeing, it looks a little different, so I can add things to this plot if I want to. And I'm like a lot of things, I always go to my little red triangle, my answer key. So I click on here, and I want to show the density curves for everything. So I'm going to click that. And I'd also like to see quantile lines. So I go up here, I go add quantile lines here. And you can pick whatever you want. I'll just use the default 10%, 50%, 90% here. And I also want to see what does the use condition look like. So I've got to grab this here, go over to 100, down a little bit, and here we go. Okay, so now you can see I know the shape of my distribution. I know the median time to failure for each distribution here, stress, and I can extrapolate that now to my use condition. So I have a complete description of my failure distribution at the use condition. This is what it's going to, again, allows me to pick off how long does it take to get to 10% failure, or what's the probability of failure by 100,000 hours or something like that. Okay. That's the Arrhenius plot. And you can also look at the probability plot, which I showed before. I'm just going to change this around a little bit. I'm going to use parametric confidence intervals. I think it looks, since I'm pretty sure this is log normal, this is going to work pretty well. I can now also show my use condition, and I want the probabilities to be more reasonable. So I'm just going to drag those down. So, okay. So here I go. And this is, again, the same kind of exercise what I would use. I can use my little pointer here. Right? And if I want to know the time, say, to 5% failure, that looks to be about 140,000 hours. Right? And I can even, with this, I can get some confidence bounds on that as well. Of course, this is, I'm doing this and it's pretty qualitative. I'm just kind of eyeballing it, right? And I don't want to just eyeball it. What I really want is, the actual estimate. So I'm going to go down here to, again, I'm getting my slope and intercept and my shape factor and my equation from U. So I can plug in whatever temperature I want, get the mu for that temperature. I know the shape factor. So for any temperature, I can predict what the distribution is. And of course, I'm going to choose my use condition. But you can do custom estimation here. So I'm just going to click on this tab. And this is where you're going to enter in the values that you want. So I'm interested in the time to, say, 1% failure. And my use condition is 100. I'm going to hit enter. And now I get my estimate. So here at the probability failure at 100 degrees C, or if the probability failure is 1% at 100 degrees C, I'd expect that to last about 100,000 hours. And I even get some confidence bounds on that estimate. And I can also, again, ask the reverse question. So maybe, again, my corporate goal might be I have to have a low probability failure at a particular time, like 1,000,000 hours or 100,000 hours. So I'm going to put in 100,000. And the temperature I want is 100. So I say, OK. And here we go. So again, after 100,000 hours at 100 degrees C, I would expect about 0.9% of my population to have failed. So maybe that's acceptable, maybe that's unacceptable, but at least you have an estimate and know where you are. Okay. Okay. So we talked about the Arrhenius model. Let's talk about the power law model. What do I mean by power law? Well, power law, I'm talking about it's a power law exponent, right? It's not that I'm hitting the part with power or something like that. The power comes from the exponent. So again, we have, for the Arrhenius equation, we had this expression, and I took logs of both sides. I'm going to do the same thing again. I have the time to failure is equal to A times the voltage to some power. It's going to be a negative value because as I increase the voltage, the failure time is going to get smaller and smaller and smaller. And I can take the logs of both sides. I'm going to have, again, an intercept term. I'm going to have a slope. That slope is going to be negative. That's going to be minus n log v. And this is going to be the form of my equation. It's going to be b0 plus b1 times x. X is going to be log v. JMP refers to this model a couple of different ways. It calls it the log model. It also calls it the voltage model because depending on the industry you're in or what literature you're reading, it's used a couple of different ways. So for completeness, JMP put both of them into the help. So what is the power law plot going to look like? Again, this is going to be very similar to what we just saw for the Arrhenius. I have in this case, 3 different voltages, 50, 75, and 100 volts. And I run tests at these voltages, and I get failure times. And I'm trying to get failure times in a reasonable amount of time. Again, we're clipping at 2,000 hours. And I extrapolate this. This is the Weibull distribution, not the log normal, right? But I'm able to get the Weibull distribution then at use conditions. And here my use condition is 10 volts. Okay? So it's going to be the same kind of exercise. And I'm going to do the same thing. So I have my probability plots. I see that as what should happen in your data is that as the stress decreases, the failure times get longer and longer. And that's what's happening here. I have at 100 volts, parts are failing pretty quickly. When I get to 50 volts, parts are lasting like 1,000 hours or so. And I'm going to extrapolate that to my use condition of 10 volts, and I'm getting some ginormous number, right? This is going to be 1,000,000 years or something like that. And I'm getting this again using this equation, which JMP has returned for me. I have my intercept term. This is my power law exponent is minus 10, and I have my shape factor of 0.4. So again, the shape factor is assumed to be constant, and that looks like a pretty good assumption here. These are all well behaved. They have nice straight lines, and I'm going to assume that slope does not change when I change the stress, and so I can make this extrapolation, and I can now predict what the probability of failure is, etc., at use conditions. Okay, and there are other models. So here I'm showing just from the JMP help. I showed the Arrhenius Celsius. Okay, we saw this expression. You can use different values of temperature. You can put it in Fahrenheit or Kelvin. Here's our voltage model where it's log of X, log of volts. Also, the log model has the same expression, log of X. But I could have a linear model. I could have a reciprocal model. You could create your own model if you want to. Okay? You have a custom model you can create. But that's just some examples of things that you can do. All right. So we have talked a lot about constant stress now, but what happens if it's still taking too long? Right? So maybe we need to get results even faster. You can when you run an experiment like this under constant stress, sometimes you have some historical values. You kind of have an idea what the activation energy is going to be. You have an idea what the shape factor is going to be, and so you can make a guess as to how long is these parts going to last, right? And maybe under these conditions, under the stresses you have chosen, it's going to last, say, a couple thousand hours, like we just saw. And you go to management and say, okay, the test is going to take 2,000 hours. 2,000 hours, that's like 80 days. That's a long time. They might say, hey, we need results faster than that. 80 days is a very long time. Can we somehow do something different and go down, maybe get the answer in a few weeks? And under constant stress, if you want to get the answers faster, you'd have to go to higher stress we're always worried about going to too high stress, and then I'm going to change the failure mode, and then my extrapolation isn't going to be worth very much. Right? So there is this another thing that JMP can do is you can do a step stress model. And this can really help reduce your test time. Again, and just like for the constant stress, we have to make sure that the stress does not get so high that the failure mode changes, right? We don't, if it does, then the extrapolation won't be worth very much. One other additional assumption is that when you change the stress, that change in stress does not have any additional effect. And I'm going to show you what I mean by that. So here's a kind of a generic step stress plot. Here is stress versus time, and I am stepping up the stress. It's kind of like a staircase. And I start at some very low stress for some amount of time. Then I quickly up the stress, and then I hold constant for some amount of time. And what we're assuming is when we change the stress like this, that doesn't have any effect at all. And that may or may not be a good assumption. So you'd have to make sure you'd have to be very confident and comfortable that if I change the stress a lot, it's not going to have some new additional influence, right? All we're going to really care about is how long it was at this stress, at this particular stress, and how long it was at this stress. Only the flat part of the stairs, not the vertical part of the stairs. And so, we're running our test, and we ramp and we ramp and we go up, up, up until finally we get a failure. Okay, that's the idea. We're going to get failures by this ramp. And here I've drawn it so that the delta t's here, the length of time spent at each step, is the same in the lab. So this might be 5 seconds or 10 seconds or something. This is 10 seconds. This is 10 seconds, all the way up until the last of a few seconds, the last step, and failed. But remember what I said before, that when we run tests at higher stress, we're changing the clock. Okay, we're making the clock run faster. So at a later step, is it basically, if this is only 10 seconds, let's pretend for a second this is the actual use stress at some early stress, early step, the delta t is 10 seconds. If I go to a higher stress, it's as if I ran it for 1,000 seconds at the use stress. Right? So basically, what I have to do is some sort of transformation or translation between higher stress and lower stress. So if I want to get the equivalent of time each of these steps is compared to the use condition, I have to do this translation. And I do that using the reliability parameters. The reliability parameters tell us what that multiple has to be. So maybe the multiple here is a factor of 100. Maybe the multiple here is a factor of 1,000, etc. Right? And so if I want to get the equivalent time at use conditions, what I would have to do is sum the equivalent time for each of these steps. So this would be 10 seconds, and I have to add, maybe this is 100 seconds, maybe this is 1,000. I'm going to add all those up at the end and translate them all to the use condition. And that translation will give me the total failure time at constant stress, at the use condition. So I can actually do a translation from a step stress test to a constant voltage test, because that's probably what I'm interested in, right? I want to know how long is the capacitor going to last at 10 volts, even though I'm running a ramp, okay? And so when you actually run the step stress, okay, you need at least 2. You might want to use 3 just as kind of a check on your data. But you're going to run a couple few different ramps, and you can now do a translation again from this ramp data to constant stress. So let me just take a step back. When I was in the semiconductor industry, it was very common to run a capacitor test and do a ramped capacitor test. You pick some fast ramp rate, like 10 volts per second or something like that, and you'd ramp a voltage up on that capacitor until it failed. And then you might do that for a lot of different capacitors. And what you want to do is find out what the failure voltage is and compare that to other batches of wafers or other designs or what have you. And you want to see, is there any difference? I want to make sure my process is in control. I want to make sure that the voltages are all the same, right? But you're never taking that data and saying, okay, well, this was the ramp rate that it failed at, I don't know, 100 volts at 10 volts per second. How long would it last at 5 volts? And the answer is you don't know because you only did one ramp. But the cool thing here is I'm doing multiple ramps. And when I do multiple ramps and I do an analysis, I can say, I can predict this is how long it's going to last at 5 volts. And also you can see some of these ramps are going to be, you're going to generate failures much more quickly than you would under constant stress, okay, because you're ramping to failure. Okay. Hope that's clear. So let's talk about step stressing a capacitor. So we're going to step stress, and you want to go up to some high level of stress, but you want to make sure you don't hit it with such a high voltage that it fails due to some other failure mechanism. So you want to avoid, 1.21 gigawatts is pretty high. You want to make sure that you don't overstress your part and so change the failure mechanism. So we're going to use the power law model again, okay? And we have our log time to failure is going to be some intercept term, and we're going to have this the power law exponent n and log b. So here are the results. I have this in a dashboard. But for JMP to do a step stress analysis, you don't just use one data table like we did for the Arrhenius. You actually have to use 2 data tables. One data table is going to give you information or give JMP information on what are the actual failure times for these different ramps. The other piece of information JMP needs is what is the step stress pattern look like? Let me just expand this. So, for example, part number 1 here had a stress pattern of 1. And you can see over here, here are my stress patterns. And the stress pattern of 1 was in red. And that's the lowest ramp rate, okay? And I'm ramping up. And what it looks like here is that this part failed after, say, 63 seconds. And it did fail, and the censoring indicator is 0. I have to tell JMP that this part actually failed. And you can see it also highlighted over here, right? You have this, this data point has been highlighted in this graph. And it looks like it's about 63 seconds. And part number 2 here also had the same pattern, pattern 1. It went 65 seconds, and then it didn't fail. And you can see here, you got the little triangle. The little triangle is telling you again that this is censored. So I have to tell JMP this was censored, and I'm telling it by putting a 1 here in the censoring column. And then I just do this, I get this for all my data, right? All my different ramp rates. And this event plot here shows me what the failure times were, okay? And I have, for the ramp rate, for the pattern of 1, this slow ramp rate, you can imagine that this is going to take a long time to fail. You're kind of creeping the stress up slowly. It's going to take longer for the parts to fail. That's why the failure times are higher here. If I go at a very fast ramp rate, like ramp pattern ID number 3, that's pretty fast. I got up to high voltage quickly, so that means that parts are going to fail pretty quickly. Okay, so let me show you how you can take this data and actually get the analysis. Right. So this is the step stress data. So I have 2 tables. Again, this is my pattern ID table, and this is my actual step stress data. So I want to do a step stress analysis in JMP. So I'm going to go to Analyze again, Reliability and Survival. And then I'm going to go up to Cumulative Damage because the damage is accumulating, right? I'm hitting it with a higher and higher voltage. It's getting more and more damaged. So the damage is accumulating. So I'm going to use this platform. And I have to tell JMP what's what. So I have to show my 2 tables. I have to show my time to event table, and I have to show my stress pattern table. Okay. So let's just do this. I click on Select Table, and my time to event is step stress. So I select that one, and I say OK. And now, like in every other platform, I've got to tell JMP which column means what. So the time to event is time. Okay. The censoring column is called censor, and my pattern ID is called pattern. Right? So I know what's what. And over here, let's see, inverse power. I don't want to use inverse power. I want to use the log model. So I'm going to click log, and we can assume the level distribution for this. Next, I have to select the stress pattern. So I select that table, and that's the kind of one that has pattern in the name. So I say OK. And the stress duration is under duration. The stress itself is the voltage, or it could be whatever, temperature, relative humidity. pattern ID is pattern ID. Right? Now I'm good. So I like this. Oh, by the way, there are other types of cumulative damage you can do. I could do a ramp where the stress varies continuously. I can do a sinusoid stress, etc. But I'm just going to focus on the step stress here today. So I say, okay. And here is the same, the same analysis you just saw. Here's my event plot. I have my failure times. I have seen parts are censored. I have information about my ramps. This is what the ramps look like, right? And I'm getting my log model, right? I'm getting my intercept term. I'm getting my power law exponent -10. I'm getting my shape factor for the Weibull. And now I have the scale parameter for the Weibull distribution. And now from here, what I can get is, again, I can predict for any X, any voltage I want. I can figure out what that mu is. I know beta. Beta is fixed across voltages. Now I can predict what the probability of failure is for whatever I want. And I can go to, say, my quantile profiler. And let's say I want to know how long is it going to last at 5 volts, right? And maybe I don't like this. I want to change this, so I can double click here quickly and just change this to a log scale. Say OK. And I can just kind of drag this down so I can see it. And it's lasting about 56,000 hours at 5 volts. Probably, so I would expect 50% of my population to have failed after 56,000 hours if I keep it a constant voltage of 5 volts. Okay, that's kind of that's where the rubber hits the road. This is where you're actually going to find out what's going on and you're evaluating your process. All right. Now I've talked constant stress. I've talked about step stress, but I've only talked about one factor. What happens if I have 2 factors, right? So sometimes you want to get a reliability map, or you want to find out, well, what happens if I have voltage and temperature? Sometimes I'm interested in knowing what's the effect of a couple of different factors, not just one. So you can imagine I ran here we go. Let's pretend I ran an experiment and I did a matrix of a voltage and temperature. So each one of these dots represents an experiment that I ran. Okay, so this was run at 30 volts and 125 degrees C, and this ran parts at 100 degrees C and 20 volts, etc. So I have data from 9 different conditions. And so what I might do is I want to plot the data just to make sure that it's reasonable, to make sure that I'm not violating any assumptions. And so what I did is I plotted these in FitLife by X, but I did this by temperature. So when the temperature is 75 degrees, I had 3 different voltages, 20, 25, and 30 volts. And I get plots that look like this. And I look at it and I say, yeah, okay, yeah, that looks pretty good. I think the shape factor is not changing. I'm not getting some sort of crazy result here. So I can believe this. And I'm going to check 100 degrees, and I get the same kind of thing. And I notice also that, say, at 100 degrees, the maximum times are around 100 hours. At 75 degrees, they're more like a couple thousand hours. Then at 125 C, I'm going to get say tens of hours. Right. So this is kind of making sense. I'm getting the right trend. As I increase the temperature or increase the voltage, I should get shorter and shorter failure times. And so what we can do, similar to what we've done before, is we want to use the quantile profiler. But look here and see, I've kind of combined now the Arrhenius and the power law, right? Now I've got 2 coefficients I'm interested in. I have my intercept term, like I did before. I have an activation energy, like I did for the Arrhenius. And I also have a power law term, which I have for the voltage, and I showed that before. So I've kind of put them all into one model, right? So now I can do, again, the same kind of thing. I can use my quantile profiler. And I want to know, for example, how long will this, how long will it take for 50% of the population to fail at 25 degrees C and 10 volts? And the answer is about 2.7 times 10 to the 10th hours, which is a very, very long time. And I even get confidence bounds on that. The lower confidence bound is about 7 times 10 to the 8th hours. And again, since this is a profiler, I can play games. I can see what would happen if we want to change these numbers. I can say, okay, what happens if I make this 50C and 20 volts? and 20 time for 10% of the population to fail. That looks like it's about 38, a little under 40,000 hours. Okay. Now, what you could do then is you could do by hand. It would be difficult, but you could put in values for temperature and voltage and then record all this, right? And to get a grid, I want to get kind of a grid of temperature and voltage, and then predict what the time to failure was. So what I did, I used actually scripting myself, and I scripted this, and I picked off for a range of different temperatures and voltages, what is the time for 50% of the population to fail, okay? And that's how I generated the contour plot. So let me show you that. Here. Oops, okay, it's not working. No save. All right. So, oops. Okay, let's go to the results. I only have a few minutes left. I'll zip through this. So here is my reliability map now. Okay, this is a contour plot. The contour plot is a 2D graph of a 3D surface. I have voltage on one axis, temperature on the other. Each of these contours means that this is a fixed time it would fail, right? This is the log base 10, the failure time. So 6 means 10 to the 6 hours or a million hours. So anywhere along this curve here, I expect the failure time to be, or it would take about a million hours for 50% of the population to fail. And I think you can see here that if I go to lower temperature and lower voltage, my time to failure is going to go up. And as I go into this region over here, higher voltages, higher temperatures, the failure times are going to go down. And so this is very interesting, I think, for, say, one of your customers or a designer, something like that. So you see that you have, this is where you're going to make trade-offs, and your designer is going to say, we want to have a new generation of parts, and we want to run at 60 degrees C. And you say, okay, fine, go ahead, run at 60 degrees C, but just don't go up to too high voltage, because if you do, the median time of failure is going to be low. It's not going to make spec anymore. Same thing. The designer or the customer says, can we run this at 18 volts? Yeah, you can, sure. Just make sure when you do that, the temperature isn't too high. You want to avoid the danger zone. Last thing is, I talked about confidence bounds. This is the estimate itself. As engineers, we sometimes like to sandbag a little bit or try to give ourselves some margin. So you could just kind of take a swag and say, well, I don't want to operate right on this line. I'm going to back off a little bit just by eye and say, okay, maybe I want to back off a volt or 5 degrees or something like that. But if you use the confidence bound, you get a quantitative estimate, right? So if I'm using the lower confidence bound, now I have a pretty good idea of how much margin I have. And now you can see that my safe operating area has been reduced, right? So now I know I can go to 60. If I go to 60 degrees C and say about 12 volts, I'm going to be, I'm still pretty safe. I can go right up to this edge and I'll be okay. Right? So ends my demo. So I think I've shown you some stuff about accelerated life testing. Shown you a variety of different models, the Arrhenius and the power law models. We talked about the step-stroke approach. It can really greatly increase the speed of the qualification of a process. And I showed you a safe operating area as a way of taking into account multiple stresses. Then it will give you a reliability map then of product lifetime. Something like a response surface from the DOE. It's the same idea.